Okay, let's get started. I'm Tucker Balch. I'm Chief Scientist at Lunar Research. I'm also a professor at Georgia Tech. And today I'm going to talk about deep reinforcement learning and how we can apply it to trading. I want to mention also that Catherine Riddick, our communications lead, is going to be taking notes, and she will be available to toss me questions towards the end. So if you do have questions, be sure to ask them on the questions tab there, and we'll get to them when we get to the Q&A towards the end. So I'm aiming for this talk to take about 30 minutes, and then we will have 10 or 15 minutes available for Q&A at the end. I'm going to start by showing you why I think reinforcement learning is a great way to treat trading problems, and I'm going to motivate that with a video game. I know that's kind of unusual, but I hope you like it. I think it actually does a good job of illustrating what reinforcement learning is and why it makes sense for trading. Next, we'll talk about how to integrate reinforcement learning with deep learning. Lots of people have heard about deep learning. It's a buzzword these days. I'll talk a bit about what deep learning is and how it makes sense to combine it with reinforcement learning. Then I'll show how we can map it to trading problems and show some results there, and then steps going forward. Now, one thing I want to preview, just a little getting ahead of things here, is actually our initial results were failures. And it's interesting, you know, to do science well, you actually have to experience failures and so on. We do see hints for how this can actually work and changes we need to make to the approach to make it work. But, you know, I want to be straight up. Sometimes when we first try to do these things, they don't work as well as we expect. And we got to keep pushing and exploring and trying different things. But anyways, let's move ahead. So Lunar Research is a leader in machine learning and predictive analytics for finance. I'm co-founder and chief scientist at Lunar Research. I'm also a professor at Georgia Tech, where I teach courses in AI and finance applied to trading. I teach a large class there and have a group of graduate students that work with me. And in fact, some of these graduate students have done some of the work that I'm going to be showing you. I want to call them out here: David Bird, Mihir Mavalankar, and Nick Patosa. Thanks, guys, for your contributions here. Okay, what is deep reinforcement learning? It's a combination of two different important types of machine learning. The first is reinforcement learning, which has been around since, I believe, the early 90s. And reinforcement learning provides a way for machines to learn what to do. So other types of learning, like, for instance, regression and classification learning, are trying to make predictions about what is the future price of a stock. Reinforcement learning is instead trying to advise you or a robot or an agent what to do. And it learns how to do this through trial and error. And an important component of reinforcement learning is that the learner receives rewards depending on how it behaves. In the same way you might train a dog, you know, by giving it a bone or spanking it, or, you know, whatever. We can train reinforcement learners in a very similar way. Deep learning is a separate type of learning that involves using neural network-based machinery that learns and stores this policy that we use with reinforcement learning. Recently, deep reinforcement learning got a lot of press when Google's DeepMind put together a Go player that could beat the world's best human. So we're starting to see now machine learning and AI techniques reach and exceed human capabilities in some sorts of tasks. Okay, here is an example of we'll call it a kind of toy problem, but as I said before, I think it motivates things pretty well. There was a video game launched in the early 80s, late 70s, called Lunar. And here's a little video of of sort of failed landings. So this is before a system has been trained. The objective, of course, is for the lander to land between those two flags. And it provides a nice, easy to understand problem in which we can consider reinforcement learning. Now, all sorts of learners have a set of inputs and a set of outputs. And for the lunar lander, the inputs to the learner are location of the lander, velocity, angular velocity, and attitude, you know, how it's sort of sitting in the air. And based on those inputs, the learner needs to decide whether it should fire the left thruster, the right thruster, the up thruster, or do nothing. Do nothing is actually a choice that it can make. And these videos, by the way, were created by Mahir, my student. Now there is one key difference, an input that is unique to reinforcement learning, and that is the reward. And let me talk about that. That's special, and that's what sets reinforcement apart. So the reward is feedback given to the agent or the learner at each step, and it's intended to help direct the agent in learning what to do. Now, in our case, for this lunar lander game, the rewards are as follows. If you land the lander between the two flags gently, you get at that point when you land a 300-point reward. That's the best you can do, is get that 300-point reward. If you land slightly to one side or another, you get only 200 points. And if you crash outside those flags, you get a negative 100 reward. So that's bad. Also, at each step, you know, if you use thrust, you're penalized 0.3 points. Now, the objective for the learner is to maximize its total reward. And if you consider each one of these components of the reward that I list above, you'll see that the learner is incentivized to, of course, land between the two flags, but it's also incentivized to land quickly because it's being punished essentially 0.3 points at each step. So again, objective is to maximize total points and essentially land between those two flags as quickly as possible. So if we take these inputs and this reward structure and we train a learner with it, here's how well it works after just some training, not full training. You can see it's doing better than we saw initially. It still makes mistakes, but it's doing a lot better than before it was trained at all. There's a nice landing. It doesn't quite know how to stop right there in the middle yet. Now, if we train it a little bit longer, it gets even better, and I'll show you what that looks like here in just a second. And be paying attention, there's going to be a quiz in a moment. Stand by for the quiz. Anyways, here's the behavior after significant amount of training. And training is essentially repeating, you know, for the learning agent, it's just repeating the task over and over and over again, observing the actions it takes and the eventual rewards it receives, and doing that many, many, many times. Anyways, it's converged to pretty nice behavior here, and on average does pretty well in this task. Now, here is the quiz I want you to be thinking about. What if we change the reward structure a little bit? Instead of penalizing the agent each time it uses thrust, what if we just, at each step, give it a small reward each step that it's alive? So the primary difference between the previous reward structure and this new reward structure is this small reward for just being alive at each step. Now think for a moment, if the agent is trying to maximize its total reward over time, what's its behavior going to be? So I'll let you think for 5 seconds, and then I'll show you the result, what it actually looks like. Okay, here we go. It essentially learns to hover. Even though it could receive that fabulous 300-point reward by landing in the middle, it learns instead, oh, and by the way, taking the chance to get that 300-point reward involves risk. You know, if it makes a bad move, it's going to crash and lose 100 points. Well, it's discovered that if it just stays alive, if it just hovers, it's going to get 5 points at each step. And it converges to this behavior where it just hovers and reaps that 5-point reward each time. I think this is really interesting because it shows that this reinforcement learner is essentially learning to weigh risk versus reward. And in this case, it's learned to accept a small reward for minimum risk. All right, so let's recap what reinforcement learning can do. We haven't talked about the deep part yet. We're just talking about reinforcement learning. But looking back here are examples of things it can do. It can learn a sequence of actions that cause it to move from one situation to another. And along the way, as it accrues rewards, it strives to maximize that reward. And we've seen that it can make trade-offs between low risk, low payoff actions versus high risk, high payoff actions. How can we apply this to trading? Well, it's a natural fit. You know, I think compared to many other sorts of machine learning, the fit here is more natural because other types of machine learning aren't necessarily incentivized for that reward. And here we've got a nice match to the trading or investment problem, namely the learner wants to maximize its return over time, and the actions, you know, instead of thrust for a lunar lander, there are things like buy a stock, sell or short a stock, hold it, or do nothing. Okay, let's look a little bit more at how that can work. One thing I had skipped and I'm going to delve into now is the deep learning part before I get to that trading part, and talk about how we integrate deep learning into reinforcement learning. As you probably know, deep learning just refers to neural network systems, and essentially we have inputs coming in here on the left, and those inputs propagate through the network according to these connections here, eventually arriving at an output layer. And at each layer, the outputs from the layer before are summed at each intermediate node here. And when the system learns, it's essentially learning what the weights on these edges ought to be. So for instance, if this input item were especially important, we would see probably large weights on its outgoing edges. And for instance, if this input were not so important, we'd probably see lighter weights on its outgoing images or outgoing edges. As the information is processed in subsequent layers of the network, eventually we arrive at a final layer, and then they're summarized in this final output layer. So that's an individual model, but we actually incorporate multiple models when we integrate deep learning into reinforcement learning. We essentially create an individual neural network for each potential action. So in the case of the lunar lander, we create 4 neural networks, one for left thrust, one for right thrust, one for up, and one for nothing. And the job of the learner is to, over time, learn the value of each of those actions in a particular state. So once the model is trained, we inject the situation, it's also called the state, you know, the input variables I talked about before. We inject those into each individual model. We look at individually what each model thinks the value of taking its action is, and we select the action that has the highest value. Okay, I recapped this already a little bit early, but on that last slide, again, I showed you how we can integrate deep learning with reinforcement learning. And again, it's about learning the value of each action. Already went through this recap of what deep learning can do, and now we'll move on to training for trading. All right. Instead now of our inputs being, describing the state of a lunar lander, in other words, where it is and how fast it's moving and so on, our inputs to the learner now are descriptions of the situation of a stock. So in the end, what we want to do is learn whether we should buy it or sell it. And to do that, we need information about the stock. So instead of how fast is the lander moving, we might be concerned about what's the recent momentum for a stock. These inputs can be technical factors, fundamental factors, they can be macroeconomic factors, and so on. And again, our actions are buy, sell, or hold. And thanks for this work to David Bird. Reward, as I mentioned before, we can use return. And in fact, you can use return in different ways. For the results I'm going to show you, we use daily return. So if you were currently holding the stock and for today the price of the stock goes up, the reward is positive according to how much the stock went up. If you're not holding the stock, you essentially get no reward whether the stock goes up or down. So that's how we adapt this model to the trading problem. So here's how we train our learner. First step is we roll back time. So we have some historical data that we want to train the system on, just like training other types of models for investing, regression, classification, and so on. It involves rolling back time and then stepping forward, step by step forward in time, training and testing your model. So here we look at this vertical blue line is the simulated time at which the model is being trained. It has access to some factors. Again, these might be technical, they might be fundamental, they might be macro. We list each factor as being x1, x2, x3, and so on. And those factors taken together, the factors describing the stock at that time, describe the state or situation. We then query our model, and the particular type of reinforcement learning we're using is called Q-learning, and the policy or model is represented in something called a Q table. So we consult our Q table and say, hey, here's the situation. What's the value of each possible action? Let me know, and I'll pick the value that has the highest, or I'm sorry, I'll pick the action that has the highest value. So in this case, we happen to choose the action buy. We look then at what our reward is going to be. Suppose in this case, we see a reward of $10 when we step into the future. We take that information and use it to update our Q table. In other words, we took an experimental action, we got feedback from the world, in this case, hey, that was a good action, and we train our model accordingly. Then we step forward again, move forward in time, repeat, and in fact, we do this over and over again over the historical data. We step forward each day, train the model, update the model, and so on. Then we go back to the beginning of time and we repeat that training. We do it many times with the intent that eventually, as we pass through this historical data, the policy won't change. And when the policy doesn't change, we say that the policy has converged and the model is essentially done learning. We can then unleash it on future data and assess it in a validation or testing time period. So that's the basic idea of how we train our deep learning models for trading. Let's take a look now at some results. Before we look at results, I want to make a brief argument for why deep reinforcement learning makes sense for trading. I mentioned this already. The learner is striving to optimize the same thing as an investor, namely return. So the objectives of the learner are well aligned with the objectives of an investor. For other types of machine learning, you have to do some adaptation to get the what the learner is doing to match an actual trading policy. You don't have to work so hard with reinforcement learning. It's directly matched to what you're trying to do. And again, these learners can distinguish between risk of loss, possible but unlikely large return versus probable small return, and so on. It learns to make those trade-offs as appropriate. And importantly, it also automatically determines entry and exit points for a stock. So in other words, say you were training a predictor that predicts a future price, and you were using that as the basis for your trading strategy. Well, you have to additionally, you query it each day and say, hey, what do you think the future price is going to be? But then you have to take additional steps to turn that output into a policy. You have to say, okay, my predictor thinks the price is going to go up 1% in 10 days. You have to somehow evaluate the certainty of that outcome and make those trade-offs to decide what to do. Not with Q-learning, with deep reinforcement learning. It tells you, it's already done the math. It knows whether it's worth it or not and directs you to enter or exit as appropriate. Now to results. So this first set of results was undertaken by my student at Georgia Tech, Nick Petosa. He built an individual model for each of the 30 stocks in the Dow 30. We evaluated this overall model of 30 stocks from 2000 to 2017. It's a long-only model, and essentially we divide our funds into 30 sleeves and allow each model essentially to trade individually over time. In terms of inputs to the learners, we used a 20-period look back, and that time series, the last 20 days, is directly taken as the input to the learner. Excuse me. Our actions in this case are long or nothing. So nothing means we're not in the stock at all. Long means we're in it. And reward for the system is daily return. Anyways, again, we evaluated this from 2000 to 2017, and here we express the results as the Sharpe ratio for each year. The benchmark, namely just the Dow 30 itself, is shown here in orange, and the performance of the strategy is shown here in blue. Now you can see for some years the strategy outperforms the benchmark, but in general we're not seeing really amazing results here. So yes, that's disappointing, and I'll talk in a moment about what I think is preventing us from doing well here. But anyways, let's just observe here that this particular experiment was not a great result. Now, interestingly, I gave this talk, up to how you've seen it now, at QuantCon. It's an annual event held in New York, organized by Quantopian. Thanks, Quantopian, for organizing that. Anyways, somebody came up to me after the talk and said, "Wow, it's too bad that didn't work, but I'm really inspired by this idea." And this guy was name is Saeed Rahman, student at Stevens Institute of Technology. He said, I have some ideas that I think might improve these results. I think an additional input to your learner ought to be it's unrealized profit and loss. So if you recall, the inputs to the models I showed you before did not include how much money you've made so far by holding the stock or shorting it or whatever. He also suggested, hey, instead of just long only, what if we consider also the potential to short a stock? And he took exactly the same approach I had showed you before. He applied it to two stocks, Apple and Exxon, and got really nice results. So this chart here below just shows you the performance of Apple and Exxon from 2010 to 2018. Exxon is here in orange, and you can see it didn't do especially well. However, his strategy showed a Sharpe ratio over this period of 1.0 versus 0.31 for the stock itself. And same approach applied to Apple, showed a Sharpe ratio of 1.2 versus 0.99. So anyways, I'll call these anecdotal results, but suggesting that there are still things we can do here, and quite encouraging, and especially nice, after having had those initially disappointing results. So key takeaways here are that pure technical data, daily technical data, may not be sufficient for daily trading, for success using deep learning for daily trading. However, as I mentioned, some anecdotal results here suggest that if we add unrealized profit and loss, that can help us, and additional inputs such as fundamentals and alternative data can help us as well. We haven't experimented with those yet, but I think that's going to be important to the success with daily trading for deep reinforcement learning. All right, let me pause now and see if Catherine has collected some questions. If some questions did occur to you over time, please put them in now, and I'll take some time now to answer them. Catherine, let me know what questions to answer.
Perfect. Thank you, Tucker. So I'm just going to start from the top of a couple ones that came in, and we'll just answer as best we can. And if you want to follow up further, please feel free to reach out via email, so we can try to get to as many questions as possible. So starting from the top, we have a big prereq for reinforcement learning systems is the want for a lot of data. What methods do you use to generate synthetic data that is similar in distributional moments to market data, not normal?
Sure. So that problem isn't special to reinforcement learning. In fact, if we were trying to do regression or classification, we have the same data. So anyways, like I said, the problem isn't special to reinforcement learning. However, there are a couple different ways you can sort of amplify the data you have. One way, for instance, is instead of building an individual model for each asset, for each stock, you can build models for, say, an entire group of stocks. So, for instance, you might train your Q-learner on each of the stocks in, say, the Dow 30 individually. So you take the model, you train it, say, for I'm just trying to think of a Dow 30 stock, Apple. Once you're done training on Apple, you take that model and you train it on the next stock, and you keep training it across all of these stocks until you reach some sort of convergence. And essentially, if you do it that way, you're multiplying your data by about 30. You are potentially losing precision in your model because you're using data from different stocks. But that's a common technique when applying machine learning to stock data. Another technique is to go further back in time. So train your model on 10 years instead of 1 year of data. Typically, though, we tend to see that best performance is achieved with shorter training periods because market regimes change so quickly. So we typically look at 3 months of we typically look at the 3 months of data instead of years of data. Okay, next question.
So Brand has a lot of great questions. We can definitely follow up with all the different ones afterwards. But some of the initial ones he asked were, have you tried using other metrics like Sharpe ratio and drawback to compute reward function? Do you use options or hierarchical Q-learning to improve generalization? And have you experimented with attentional networks to improve performance?
Okay, good questions. We have used so far only return as our reward function. I think that it'd be interesting to try others, and they may work. But the way if you look in the way Q learners work, they're trying to maximize discounted reward over time. And what they're trying to maximize actually is, I mentioned that they're trying to maximize total reward. That was a bit of an oversimplification. What they're trying to maximize over time is discounted reward. And this actually corresponds pretty closely to Sharpe ratio. However, training to other potential reward functions, I think, offers a lot of promise and is worth exploring. We haven't explored it yet. What was the next question of those questions?
Let's see. Do you use options or hierarchical Q-learning to improve generalization?
Presently, no. But I think those approaches could make a lot of sense. We used more or less just very basic technique like the ones I illustrated in the talk. Next question.
Lee asked, what's the benefit of 4 separate deep learning models instead of a single model that outputs the same 4 outputs?
Yeah, that's a good question. It is getting a little bit technical, but let me go back to the slide that I think he's probably talking about. Let's see here. Okay, here it is. So here we created a separate model for each potential action, and in training, we train them each individually. What we discovered is the following: is that, and again, this is technical. If you've been doing deep learning, it may make sense to you, but don't worry if it doesn't. Anyways, when you go to do your update, to do your back propagation, the Q-learning update rule specifically gives you a value for the state and action that you just took. So let's suppose we had just used left thrust and we got some sort of feedback for having done that. Well, you have information only really for having done left thrust. You don't have information to update these other actions or components of your Q table. So we elected to just feed back to the particular model that had caused that output, because that's the only one we have information about. There are other variations of this that you can use that are similar, but this one turned out to be very efficient and converged nicely. Okay, next question.
Okay, so we'll try to answer 2 more. Let's see. Ryan asked, have you systematically evaluated different look-back/forward return horizons? Have you tried one model for all stocks?
So we follow procedure that we follow for all different kinds of models that we create, which is namely we a priori identify a period for training and then a period for out of sample validation. And we iterate over and over those periods while trying different meta parameters, like how far do we look back when we train and so on, to determine our, like I said, our meta parameters, like how far to look back. We then evaluate that particular choice of model settings in a validation period. And we repeat that until essentially we find the best set of parameters for building our models. We always maintain, after that validation period, a holdout set where once we've discovered the parameters we ought to use, we then use them for training a model, and we test it in this holdout set. And usually we see it working well in that holdout set as well, and if it does, then we say, okay, this is a good set of hyperparameters for our model. Next question.
Philip asked, how would you compare deep reinforcement learning with genetic programming, example, genetic algorithm? Could you somehow integrate them both?
Sure. It's an interesting question. It is true that okay, so let's think about what a model is in genetic algorithms or genetic programming compared to reinforcement learning. In both cases, they can output a policy. Namely, it's something that tells you what to do in a certain situation. So if each one of these learning techniques you think of as a black box, they are both trying to optimize the same thing, namely to find a policy that will maximize your reward over time, or your Sharpe ratio, or whatever you want to measure. So indeed, they are striving to solve the same problem. They're just using different techniques for searching the space of possible policies. My intuition is that deep Q learning sort of provides a more focused search than genetic algorithms. But I wouldn't a priori say that one is better than the other. I happen to have a lot more experience with deep Q learning than genetic algorithms for solving these problems. I would also say there's probably a little bit stronger mathematical foundation for them, but indeed they solve the same problem, and I think it would be a worthwhile exercise to look at how you might use genetic programming to solve these problems. Okay.
So I think we maybe have time for one more question. This will be the final one. So David asked, how can interested individuals begin building experience / skill sets in the field of predictive analytics and finance?
Well, I think the best answer is take my course at Georgia Tech. It is available online for free. It's offered through Udacity. So go to udacity.com and look up Tucker Balch class, and you'll find a class I give on machine learning for trading. And in fact, the students that contributed to these slides that I just provided had taken my class in the past. It's a good preparation for doing this. And also stay tuned to Lucena. We put out a webinar every few weeks, and we also have a history of lots of interesting webinars. The last one was about using convolutional neural networks for investing. That was by our CEO, Aris Katz. Thought it was a really nice, informative presentation as well. Anyways, good luck with that, and contact me at Georgia Tech if you're interested in pursuing some of those things.